Hello, my name is Robert Mitchell, and today Electropages is here at PCIM Nuremberg 2024, and we are with SemiQ, and I'm joined by Dr. Timothy Hahn. Thank you for having us today.
Nice to meet you.
You too. Thank you. So, everything is about power today, and we've got some really cool looking stuff here. So my first question to you is, what's going on with your company, and what do you provide for power solutions?
Okay, nowadays wide bandgap is the most popular in the world, and SemiQ is provide the silicon carbide power device solutions. So we are developing our own silicon carbide MOSFET wafers, as you can see here.
Right there.
Yeah, so it's this is our bare die. So basically, what we're doing is we grow the wafers. And then we screen out the potential weak device, and we select only the good die.
Oh,
yeah. So it's a gate burning and the vapor probing, testing. Once everything is done, we create this, regenerate this kind of good vapor.
And so even though some of those dies might be working,
yeah,
if they don't fall within spec, you discard them, and you only choose the ones that have the absolute best characteristics.
Yes, absolutely. The critical pieces is reliability and the quality, of course. So without screen out the weak device, the field failure is very obvious. So it's screening the good device is extremely important. Once that is done, and then we put into the package.
And the package is coming up here. Yep,
yeah.
Here we go.
So you see there's a small package. It's called the Topside Cooling package. This is the one.
Oh, Topside Cooling.
Yeah. So it's a TC pack, TS pack, it's Topside Cooling package. And then our standard is a 20247 3-liter the poly, and the 20263 7-liter package is for our discrete product portfolio.
And so that topside one's quite interesting. So that metal pad, you can attach a heatsink to with some thermal bonding compound, and that will help take the heat out.
Correct. So it's a heat dissipate to the top. We have two versions. One is
on the bottom as well.
Electrically isolation, and the other one is electrically non-isolated.
Right.
Yeah.
So one could be a grounding pad,
correct.
And then the other one's your heat dissipation.
Yes.
Oh, fantastic.
So, yeah, that's the new one for especially targeting for automotive application. You see the e-compressor.
Oh, this one here.
Yeah, e-compressor type of things. The onboard vehicle charger. So that's the way we can put this Topside Cooling package.
So I can also see some boards here that look like they have the chips directly bonded to a sort of like a circuit almost. The ones that are number 2 and number 1, I think. So what's going on there?
Okay, so the modules, so we have a paralleling multiple MOSFET inside.
Right.
So for the sake of argument, the one you saw, that one is our E7 module package.
Yep.
So that one have like 6 MOSFET in parallel.
Yeah.
So it's a total 12 MOSFET inside one package. So it carry on up to like a 600 ampere current rating.
600 amps?
Yes.
At what voltage?
1200 volt.
I have to do the math in my head here. Hang on a second. So 600 amps,
yes.
1200 volt, 1000 be 12, maybe about 8 kilowatts or so?
No, more than that. No. Much more than that.
80 kilowatts?
8 kilowatts.
Oh my, 80 kilowatts?
Yes.
So this is a really good example. So I was actually talking to Jack earlier. He asked me at PCIM what do you think is the most powerful device here. And I said to him, you might be surprised. It's not necessarily going to be the biggest thing you see. You might find something like this, which is potentially up to 80 kilowatts in a module that size, which is insane. That's powering what? 8 to 10 homes easy in terms of like the raw power, in terms of raw power capability.
Yeah, so I think the point is, in order to achieve that high quality of that inside that module, so we have to select the right device once again,
devices.
And then we put that one in the parallel into the package.
Yeah.
So we provide this 62 millimeter height conventional module, but we make the module is low profile. So the switching loop inductance in the power loop reduced by half.
Oh,
so it's about 8 nanohenry. Compared to the full height, you see that.
So that's the full height there.
Yeah, full height,
that's
half height.
Yeah.
Full height version is about 13.5 nanohenry loop inductance. Right. But so by doing that, you reduce the voltage spike. So it's inductance L times di over dt.
That's right.
Create the dV/dt, right? Voltage spike. So you can reduce the voltage spike and you can reduce the EMI noise.
Oh, because that's also important as well, because I can imagine that when you're switching such a huge amounts of current very, very quickly,
Yeah.
like you say, you're going to get, if you've got too much inductance, you're going to get voltage spikes as a result of the falling magnetic fields. You're going to have issues with, in terms of, I suppose, current draw as well, in terms of heating. So by choosing, by being very selective of the device you choose in your wafer, you can maximize the performance of your power modules while minimizing resistance, maximizing efficiency, and reducing EMI and all those transients. So, so what kind of efficiencies are we looking at if we were to use this in a power converter?
So it depends on the applications and converter topologies and the switching mechanism. There's hard switching and soft switching, and also switching frequency also changing from 10 kilohertz to 100 kilohertz.
Yeah.
So it's hard to say specific number.
Because it depends on the design
Yeah.
they're using. So,
Correct.
so it's not really the device that's important there. It's the whole design. And so from that question, I suppose what I would ask is, when it comes to, so if you're going to use this in a switching application, how would a design engineer make sure that their design is as efficient as possible when using silicon carbide?
So in order to maximize the benefit of silicon carbide switches, so it's optimum design, especially the gate driver circuit.
Yeah.
And also it's combining with all the even passive components, including the filters and the transformers. Is the right selection of the other power component is very important. So we are recommended to work with our design team and application team to optimize the design.
I was literally about to ask you that. I was going to say, because it's quite obvious, it's quite evident that you are producing high quality devices, but the device is only as good as the design is put in. So, as you just said, engineers want to maximize the use of your parts, call you guys up, and then you can actually help with that design overall, which is great to know, because if I remember correctly, silicon carbide, it's a bit more tricky to use compared to traditional silicon in terms of gate driving. Is that correct?
Yeah, it's a lot more sensitive because there's a higher DIDT or DBDT.
Right.
So it's a common mode noise rejections from the gate driver side to the switching side. So you have to have well isolated in between.
Right.
And also it is very sensitive to the PCB design, especially capacitance between the gate and the drain side. So if you have any parasitic capacitance in the your circuit design between the gate and drain, it significantly changes the switching behavior.
Right.
So those things have to be also one of the concerns.
And what kind of switching frequency can these types of silicon carbide devices switch up to?
So for the module, we specify exactly what is the maximum allowable switching frequency in our data set. So usually from couple tens of kilohertz up to 500 kilohertz, you don't have any problem.
Right, I mean, that's really fast considering it's able to do up to 600 amps, like you said before. So so using that, I take it an example of an application where it might be quite useful would be automotive charging.
So for the sake of argument, like the DC-DC converters and the LLC topology, you just use about 100 kilohertz, 200 kilohertz
Right.
switching range.
Yeah.
But if you wanted to do like induction heating, so conventionally people use the IGBT with the interleaved structure.
Right.
So it's a 300 kilohertz or 400 kilohertz, even 600 kilohertz. But now you use the silicon carbide instead of interleaved structure. So you have even single switch can go very high frequency.
When you say induction heating, are we talking cookers, or are you talking like induction coils when you do heat treatment of metal parts?
Something like a melting pot in the
like the crucible inside.
Yes.
That makes sense. And so it's just because of its ability to switch high frequency but also high current, it can give you high efficiencies in those applications and therefore more, well, I suppose, easier to operate.
Yeah.
But what I think is the most impressive thing is the size of these parts. So we've got these chips here on this wafer,
Mm-hmm.
and these are individual silicon carbide MOSFETs. How much current in each one of those chips?
So this one is carrying easily about 100 ampere.
Oh my goodness. 100 amps?
Yeah. So
Let's just wait for it to come back round one more time. So these little tiny chips, right here, each individual one, which is smaller than my fingernail, is 100 amps.
yes,
And voltage-wise, 1200 volts?
1200 volts.
1200. So that's 12 kilowatts per chip.
Yes, that's what I'm saying. We have 6 in parallel.
And that's why my numbers were off by a factor of 10. It's really hard to comprehend that something, and it's so thin as well.
Yeah.
So what is it about silicon carbide that makes it so able to handle so much current?
So it's basically silicon carbide is this is MOSFET structure. It's not IGBT, bipolar structure. This is unipolar structure.
Silicon carbide is bipolar.
No, it's not a bipolar.
It's this MOSFET,
This MOSFET is a unipolar.
Oh,
But
right.
it's compared to the IGBT have always a cut-in voltage.
That's right.
But this is like a linear device, number
Right,
one.
right.
This is very efficient in the light load condition. But at the same time, the quite significant improvement over channel resistance now, and then the chip size is small, but it carry on the much higher current.
And that also means that, for example, number 11 there, that could do 100 amps as well.
Yes, but
Not number 7, surely.
number 7, no.
No, that would be insane. That would be way too small for 100 amps. But so you've also got some other components here, which look like power resistors. So what's going on here as well?
But this one is our partners, and Alphatech is have like a handling, not just the power switches, and they also handling power discrete and inductor and other things. So we share this podium.
And so these are components that you'd also recommend to use when handling your silicon carbide devices.
Yeah, so this is not our product, but Alphatech needs support.
It's almost partnered with each other. So Royal Ohm provides resistors and resistor solutions that will work well with your silicon carbide devices, which I still can't believe that's 100 amp per chip. That's honestly ridiculous. So just before we wrap up this video, I've got one more question for you. For the viewers out there who are watching this video, if they want to get involved with your silicon carbide devices, what would you recommend that they do?
Sorry, I missed.
For the people who are watching this video, if they want to get involved with your silicon carbide devices, what would you recommend that they do?
So I think nowadays power electronics engineers are getting used to do or to use the silicon carbide power device. And even though it is a much faster device, they may be struggling with, as I mentioned, the noise issues and managing all the circuit and the component. But this is a natural trend. Have a higher density and a higher power, a higher efficiency, and a lower cost too. So if you are like a power electronics engineer, absolutely, it's coming few years, you should touch this component, and you have to migrate from silicon device to silicon carbide. Yeah.
And so, if they want to, let's say they want to buy some of these parts, where would they go to buy?
We have like a DigiKey, Mauser, all those DigiKey, and also you can direct contact to our sales network through our website. You can order a sample, and we can contact to you.